In this section, we'll discuss clothing systems that allow humans to live and work outside of a protective habitat or spacecraft in extraterrestrial environments. As we discussed in the extraterrestrial environment section, the hazards of living outside of Earth's atmosphere are significant. Extreme temperatures, low pressures, lack of oxygen, radiation, micrometeoroids, and reduced gravity all make living and working a complex and challenging problem. As with any other functional clothing problem, the key challenge is managing to provide functional protection while still allowing the individual to accomplish the reason they're in that environment. In other words, to make sure the person can live and work at the same time. In this section, I'll focus mostly on U.S. spaceflight activities and the systems that NASA built to support life in space. But bear in mind that other space agencies around the world, particularly the Russian Roscosmos Agency, were also developing these capabilities at about the same time, using different approaches. This timeline shows some of the major missions that drove the U.S. spaceflight program. The 1960s was a period of rapid growth. The Mercury program first launched humans into space, but they stayed inside of the spacecraft the whole time. The Gemini missions came next, although the Apollo program was technically started before Gemini. And Gemini astronauts were the first to go outside of their spacecraft. The Apollo program's mission was to land a person on the moon and return them safely to Earth, so it was the first time that humans had walked on a surface other than the Earth's. After Apollo, the Skylab program launched the first orbiting habitat where humans could live and work in space. In 1981, the Space Shuttle program was begun to transport people and equipment more frequently into space so that the International Space Station could be built. And in 1998, the space station was occupied by its first crew and has remained in constant operation ever since then. In 2011, the US retired the space shuttles, which could carry up to 8 people at once. Instead, crew members now travel to the space station in the Russian Soyuz capsule, which is much smaller and can only fit 3 people. When humans first started looking at traveling to space, the closest environment that had been explored was the deep ocean. Deep-sea diving suits were almost like person-shaped submarines, big metal suits with joints that allowed a little mobility. This example from the early 1900s had to be moved with a crane. One of the hands can be fitted with a lamp, as you can see here. As you can imagine, mobility was a challenge in this kind of suit. Instead of gloves, the wearer used this robotic grasper to pick things up. Picking up a pin with this kind of device might be an exaggeration, though. Deep-sea diving suits are designed to protect the wearer from the extra pressure experienced at the bottom of the ocean. On the other hand, as you get farther up, away from the Earth, pressure decreases. Early pressure suits for high-altitude flight looked a lot like deep-sea diving suits and were based on similar concepts. Wiley Post, one of the first high-altitude pilots, used this suit made out of rubberized parachute fabric with a metal helmet. The suit was supplied with oxygen from an external tank and was pressurized to 7 psi, or pounds per square inch, which is about half the pressure you'd experience at sea level, but almost twice the pressure of current spacesuits. The idea of a pressurized suit is that you're essentially creating a space around the body and filling it with a little atmosphere that's like what you'd experience on Earth. Soft, fabric-based suits are lighter weight and more compressible than rigid metal suits like the deep-sea diving suits, but they have their own challenges. When you inflate a non-stretch fabric with air, it becomes very rigid and difficult to bend. It also expands as far as it's able to. Here you can see a Project Mercury spacesuit and how puffy it gets when it's fully inflated. Inflated suits also have a tendency to grow, so straps like this one are used to tether the suit from top to bottom so that when it's inflated, the helmet doesn't rise up and make it difficult to see outside of the suit. When the suit is unpressurized, you can see some of its mobility features. Nylon straps were sewn to the suit to hold areas of gathered and pleated fabric in place, so that when it was pressurized, the joint would bend into a more mobile position. Here you can see what it looks like when the suit is blown up without anyone inside. This is the position the suit is designed to take when it's inflated. The reason that it's hard to bend is that bending a joint causes that inflated tube to buckle and change shape. The overall volume inside the suit is decreased, which increases the air pressure. So the wearer has to fight that increase in pressure in order to make the suit bend. This suit may not look easy to move in, and it wasn't, but remember that these suits were designed to be worn inside a pressurized spaceship, so they were really only there in case of emergency, in case the capsule lost pressure. Mercury suits were also attached directly to the spacecraft. You can see here the long umbilical tube that's coming out of the suit. This gets attached to the spacecraft to deliver air to the suit both for breathing and to keep the crew member cool. Mercury suits were cooled with air only, and they used nylon coil spacers underneath the suit in the chest, the upper arms, and the upper legs to help air move around the body. Crew members wore long cotton underwear underneath the suit to help with sweat and moisture. In the Gemini program, spacesuits had to protect from a lot more than the Mercury suits did because the crew members were going to go outside the vehicle. Here you can see astronaut Ed White on the first U.S. spacewalk, or EVA, extravehicular activity. Like the Mercury suits, his suit is still tethered to the spacecraft to supply air. But because he no longer has the walls of the capsule to protect him, his suit now needs to deal with some new hazards of living in space: temperature, radiation, and micrometeoroids. In space, the Earth's atmosphere doesn't protect from the extreme temperatures we discussed in the extraterrestrial environment section. The bladder layer that holds air pressure around his body is now underneath an oversuit, which is designed to protect from these new hazards. The outer layer of this suit is white to reflect the sun's radiation. Underneath that is an insulating layer of felt, followed by many layers of aluminized mylar film. The mylar is highly reflective, so it will also reflect radiation away from his body. It's also there to slow down and break up any tiny flying micrometeoroid particles that might hit the suit before they get to the bladder layer that's holding the air in. Gemini astronauts were definitely going to have to move around in pressurized suits. For Mercury astronauts, the hope was that they wouldn't need to do much of that. For better mobility, the Gemini suits used a new concept. The neoprene rubber bladder layer that kept air pressure around the body was restrained using a net of interlaced nylon cords called link net. This net allowed the volume of the suit to shift around more without ballooning outwards. Inside the pressure suit, air channels built of stainless steel coils were used to move air around the body to cool it down, similar to Mercury. For the Apollo missions, mobility became a really big issue. The Gemini astronauts had to be able to get in and out of the spacecraft and move around a little while they were floating in space, but Apollo astronauts were going to need to climb down ladders, walk around on the moon, bend down and pick things up, and be able to fall over and get back up again. None of those things would have been really possible in older suits. However, a promising concept for mobility had been explored in the development of much earlier pressure suits. Joints like these, called constant volume joints, had been developed in test suits. They used accordion-pleated rubber convolutes that could contract and expand as the joint moved. Combined with restraint cables running along the length of the joint could maintain a constant volume when it was moved by expanding as much on one side as it contracted on the other side. For earlier missions, they were too bulky to fit inside the cramped mission capsules, so that's why they weren't used. But for Apollo, this concept was expanded and refined into slimmer, lower-profile rubber and neoprene joints that were used to allow mobility at the ankle, the knee, the hip, the shoulder, the elbow, and the wrist. The bladder layer also used a restraint system based on nylon tunnels and cording, some steel cables, and lacing adjustments. Altogether, this allowed the astronauts to move enough to accomplish their exploration task on the moon's surface. However, for later Apollo lander missions where crew explored farther away from the landing site, they used a lunar rover vehicle to get around. The previous Apollo suits had been cut more or less in the standing position, and it was difficult for crew to sit down in the vehicle. So these suits had to be adapted to allow for the seated position. The seat was made wider, and a waist convolute was added. The entry zipper that had formerly passed down the back and between the legs was moved over to the side. And a new adjustment had to be added to the helmet tie-down strap. Remember that crotch-to-shoulder strap that was used to keep the helmet down on the shoulders when the suit was inflated? In the seated position, the helmet rode up and over the field of view more than it would when you were standing, so it needed to be cinched down while the crew rode on the rover and then released when they stood up. The Apollo suit was made to protect from a lot of the same hazards as the Gemini astronauts experienced, with the addition of one more: moon dust, which we'll get back to in a minute. The Apollo suit used the same multi-layer concept as Gemini did, with a pressure suit covered by an oversuit that protected from temperature and micrometeoroids. This suit used more than 20 layers of material, including Teflon-coated beta cloth, which is a woven fiberglass fabric, multiple layers of alternating aluminized mylar, Dacron, and Kapton film for insulation, and a new material called Chromel R, which is a woven stainless steel fabric that was used for protection from abrasion, micrometeoroids, and puncture while on the lunar surface. Inside the pressure suit was the layer meant to keep the astronaut cool, but unlike Mercury and Gemini, it couldn't really just rely on air flowing around the body. In fact, during one of the Gemini EVAs, the limits of that cooling approach were seen when the astronaut's visor fogged up with body moisture from overheating. In the extreme environment of the moon, when crew were working really hard to move that suit around, a different approach was needed. The Apollo suits used a liquid cooling concept where instead of air flowing through coils and spacers, tubes carrying cold water were routed around the body. But remember that for Apollo, unlike Gemini, the astronaut could no longer be tethered to the spaceship for air or water. All of that life support had to be carried around with them. The Apollo suit integrated with the Portable Life Support System, or PLIS, which was carried around like a backpack. It took care of cooling and pumping water through the liquid cooling garment, as well as moving clean air into the suit and taking old air out of the suit to be cleaned and reused. It also regulated the suit's pressure. Altogether, the suit with the PLIS weighed about 189 pounds. Apollo missions were much longer than previous missions, and the capsule and lander were a lot larger. Crew could take off their pressure suits and wear indoor clothing inside a capsule or a lander. Either the cotton long john underwear that they wore underneath their suit, or a Teflon-coated jumpsuit that they called a constant wear garment that you can see here. Outside the lander, the suit had to deal with a new hazard, moon dust. The surface of the moon is covered in pulverized meteor rocks, which makes a fine dust that's very, very abrasive and also somewhat magnetic. It stuck to the surface of the suit and it wore away at surfaces and bearings and metal components. Higher abrasion areas of the suit included a layer of Chromel R, that stainless steel fabric, that was first introduced in Gemini suits to help with micrometeoroid protection. To help protect the feet, the lander suits had overshoes that included Chromel R uppers, a lining made from beta cloth, and 13 layers of alternating aluminized mylar and Kapton film for insulation. The soles were made out of blue silicone with 2 layers of beta felt between the layers of Kapton film for extra temperature protection. Suits similar to the Apollo suits were used for Skylab missions and for subsequent spaceflight between Apollo and the start of the Space Shuttle program. But the shuttle program was the next big shift in suit design. In the intervening years, however, many different suit concepts were explored by NASA and by other groups, including the U.S. Air Force, who were interested in developing pressure suits that would allow engineers to get inside of vacuum tubes that were used in electronic systems in order to do repairs. Pressure suits used on Earth didn't have to take into consideration the challenges of packing and shipping a suit up to space, so they could explore really different options. One of these alternatives was a hard suit concept made out of rigid materials. These suits might look more similar to the early diving suits that we saw rather than the Apollo spacesuits. Most hard suit concepts operate through stovepipe joints where asymmetrical sections roll and rotate on bearings to allow the joint to take different positions. Another concept that was explored by NASA was the mechanical counterpressure suit. This was a skin-tight suit that holds pressure on the body by squeezing it with fabric rather than by pressurizing air around it. This suit used 7 layers of fabric, mostly a strong elastic power net, that were stretched tightly around the body. It was successfully tested in a vacuum, but because it was so difficult to put on, it wasn't pursued. The spacesuits that were developed for the Space Shuttle program are still used today on the International Space Station, and the full assembly is called the EMU, or Extra Vehicular Mobility Unit. Like the Apollo suit, the suit is still 3 main components: a liquid cooling and ventilation garment inside the suit, a bladder and restraint that holds the air pressure, and an outer suit that protects from thermal and micrometeoroid hazards. The pressure suit layer is a combination of hard and soft segments. The upper torso and lower torso are rigid fiberglass shells, to which soft arms and legs are attached. Because the suit is modular, it doesn't have to be custom fit to the crew member the way that the Apollo suits did. Crew members can pick the best size for each module and then adjust them using draw cords and other adjustments on the restraint layer. The layers of the EMU are similar to what was seen in the Apollo suits. Nylon knits for the liquid cooling garment, a bladder made of urethane-coated nylon with Dacron restraints, and the thermal micrometeoroid garment that uses multiple layers of aluminized mylar covered with a layer of orthofabric, which is a blend of Gore-Tex, Kevlar, and Nomex. The current liquid cooling garment is very similar to the one worn by Apollo astronauts. It contains a network of tubes that are routed around the body through a mesh layer that holds them in place. Inside the liquid cooling garment, the crew wear a comfort layer of clothing, and they also wear an absorbent garment, or diaper, to collect any liquid or solid waste they might produce during a spacewalk. The suit is donned in two pieces. The lower torso is put on like pants, but with the boots attached, and then the upper torso is sort of like a big shirt. They're joined at the waist, and then the helmet and gloves are attached later. Dressing in a spacesuit takes about 45 minutes, and once it's on, the crew spend about 2 hours pre-breathing pure oxygen to get ready for the lower pressure environment inside the spacesuit. Less pressure than you'd experience on the Earth allows the suit to be moved and bent more easily, but it would also give you the bends, just like scuba diving would, if you didn't pre-breathe oxygen and allow the nitrogen to leave your bloodstream. Shuttle astronauts also wore another spacesuit, the orange one that you might have seen them wearing in portraits or on their way to a launch. This is the Advanced Crew Escape Suit, or ACES, a pressure suit that's worn only during launch and landing to provide pressure in the event that the vehicle loses pressure. These are closer to the Mercury suits than anything. They're meant as a backup in case of a disaster. The pockets on the suit are filled with survival equipment. Space Shuttle crew members these days perform EVAs mostly to do repairs on and around the space station. Earlier in the program, they were actually building the station. So the suit really exists to allow them to do this work. Unlike Apollo astronauts, they really don't need to walk. The moon has some gravity, but the space station is orbiting, so the crew are really floating while they do their work. Their legs are more for stability than for mobility. They use them to hold themselves in place. Because they're working, they also need to carry tools, parts, and equipment with them. These are usually carried in pockets on the legs and in a tool belt that's worn around the waist. Everything has to be contained or tethered to the crew member. If you drop your screwdriver, you might never see it again. Although they're always close to the station is very, very big, and they can travel a long way from the airlock during an EVA. So tethering the suit to the vehicle, like the Gemini crew did, wouldn't really be possible. Space station crew also wear a portable life support system in a backpack, just like the Apollo astronauts did, that controls the temperature and pressure in their suit. During a spacewalk, the astronaut needs to keep track of a lot of information. Part of that is about monitoring the suit itself, keeping the temperature comfortable and watching its pressure. The controls for the suit are located on the chest, and because the astronaut's head is inside of a helmet, they can't really look down at their own chest. So a wrist-mounted mirror is used to see the suit controls, and all of the text on the front of the suit is printed backwards so that it can be read in a mirror. The crew's activity during an EVA is orchestrated down to the minute, and their procedures have been rehearsed for months before the mission. To keep track of all these tasks, the crew wear a cuff checklist that contains all of the procedures for their EVA. This was also done for Apollo missions. Another visual cue that crews need during an EVA is who. All spacesuits look alike. This first became a problem during the Apollo missions, the first time that two astronauts might be moving around outside at the same time. The solution that they used then is the same solution we use now. Red stripes on the arms and legs indicate the lead crew member. For Apollo, this was the commander, and they were known as commander stripes. But for current astronauts, the red stripes indicate EV1, or the lead astronaut on the EVA. EV2, the second crew member, has no stripes. There's only ever been one 3-person EVA before, but EV3 would wear red and white candy stripes. To communicate with the ground, inside the helmet is a communications carrier assembly cap, known as a Snoopy cap because of its coloring. This was first used for Apollo missions. Earlier missions had speakers and microphones built into the helmet, but that meant that the field of view was narrower. When you turned your head, you might see an ear cushion and a speaker instead of the visor. Putting the communications on the head directly means that it moves with the head, so you can have a larger field of view. The last piece of spacesuit experience that I want to emphasize is the part that astronauts spend the most time on, training. For several years before a mission, crew train on every detail of their mission experience. This includes EVAs. EVAs are rehearsed for hundreds of hours in a special training facility called the Neutral Buoyancy Lab, which is a big swimming pool that has a replica of the space station at the bottom. The astronaut is weighed precisely so that they experience neutral buoyancy. They don't float or sink in the water. These long hours of training are where a lot of astronaut injuries happen. The suit is difficult to move, and it results in a lot of difficult physical strain. Abrasion and bruising between the edges of the hard upper torso bearing, as you can see here on the left, and between the liquid cooling tube manifolds and the hard upper torso in the back, as you can see on the right, are very common injuries. Astronauts also experience rotator cuff injuries from moving the suit arms around, and some even have fingernails fall off because of the forces and moisture buildup in the suit glove. These hazards are indications that there is still development to do on spacesuit design.